Hi, let's discuss the problem on regenerative Rankine cycle. The simple problem. Let's understand the problem statement. A steam turbine is fed with steam having an enthalpy of 3100 kJ per kg. It moves out of the turbine with an enthalpy of 2100 kJ per kg. In regenerative Rankine cycle, we know that we have the boiler. So from the boiler, we are taking out the steam at state 1. So here the steam turbine is fed with this steam, so whose enthalpy, that is H1, is 3100 kJ per kg. So this steam enters the steam turbine stage 1 and comes out at state 2 here, so then it further expands in other stages of the turbine and comes out at state 3. So here it moves out of the turbine with an enthalpy of 2100 kJ per kg. So here the enthalpy out of the turbine is H3 here. So he has mentioned it as 2100 kJ per kg. Feed heating is done at a pressure of 3.2 bar. Means we have the feed water heater. The feed water heater OFH I am writing. So feed heating is done at a pressure of 3.2 bar. So this is 3.2 bar pressure line because feed heater is supplied with the steam at a pressure P2, so that is P2 is equal to 3.2 bar. The steam with an enthalpy of 2500 kJ per kg, means the enthalpy of this steam which is supplied to the feed heater H2 is 2500 kJ per kg. So now here the condensate from the condenser with an enthalpy of 125 kJ per kg enters into the feed heater. So here the steam after coming out of the turbine at state 3 enters the condenser here. So the condensate comes out at state 4. So then it enters a pump. So from the pump it enters the open feed water heater. So 4 to 5 is pumping process here. So that is H5, that is HF5 is 125 kJ per kg. The condensate from a condenser with an enthalpy of enters the feed water heater. The quantity of blood steam is 11,200 kJ per kg per hour. The quantity of steam means in 1 hour, so we are bleeding 11,200 kg per hour. That is 11,200 kg of steam is bled from the turbine and supplied to the feed water heater in 1 hour. We need to find the power developed by the turbine. Means this is the turbine. So this turbine is able to generate the power for us. So this power he has asked to calculate. Assume that the water leaving the feed water is a saturated liquid. Means the water which comes out of the feed water heater is a saturated liquid and it comes out at same pressure of 3.2 bar. the heater is mixing type. Mixing type means the saturated liquid which has come out from the pump at state 5 and the steam blood from the steam turbine, so both gets mixed. Such type of heater we call it as a mixing type, and we have already discussed this concept. So now here we have the pump, so which pumps this condensate into the boiler. So here the outlet of the open feed water heater is state 6. So from pump it enters into the boiler at state 7. So this is WP1 and this is WP2. So he has asked us to neglect the pump work, and he has asked us to calculate the power from this turbine. So now we are supposed to calculate the power produced by this turbine. So here we know that we assume 1 kg of steam is flowing into the steam turbine, and we are bleeding m kg out of this, and 1 minus m kg blows into the remaining stages of the turbine. So inside the condenser 1 minus m kg, same 1 minus m kg is flowing, same 1 minus m kg enters the feed water here. So here m kg is entering the open feed water here to here. So that is 1 minus m, then 1 more m plus, both cancels, so hence 1 kg, the same 1 kg will come out here. So this is the given data for the present problem. So we are supposed to calculate power, and for power developed, we know that power is always net work developed in the cycle into mass flow rate of the working fluid, that is m dot s. So s for steam here, so where m dot s is mass flow rate of steam. So now if we want to calculate the net work developed in this cycle, so that is nothing but total turbine work developed in this plant, and the pump work is subtracted out of that. So the total turbine work developed is, so we can say that this is the first stage of the turbine, this is second stage of the turbine. The work developed by the first stage is WT1, the work developed by the second stage is WT2, and the total work developed is WT is equal to WT1 plus WT2, we can write. So here, so therefore the net work is power is equal to turbine work, total turbine work minus pump work into m dot s. So in the problem statement he has mentioned that the pump work is to be neglected. So here WP we consider it as a 0 because it is to be negligible. So then hence power developed is turbine work into mass flow rate of steam. The total turbine work is again, so as we have discussed in the schematic diagram, the total turbine work is WT1 plus WT2. So here that turbine work we will calculate in this equation. So therefore I need the turbine work, So for turbine work, WT is the turbine work developed in the stage 1 plus the turbine work developed in the stage 2. So here the turbine work developed in the stage 1 is nothing but H1, that is inlet enthalpy minus outlet enthalpy of the stage 2 multiplied by the mass of steam which is flowing inside the stage 1. So that is 1 kg of steam is flowing inside the stage 1, and the inlet enthalpy of stage 1 is H1 here, and outlet enthalpy of the stage 1 is H2 here. So that is H1 minus H2 is the change in enthalpy during stage 1. So I will write now H1 minus H2 plus the second stage, work developed in second stage is the quantity of steam flowing inside the stage 2 is 1 minus m kg, because I had bled m kg after stage 1 and remaining the steam was 1 minus m kg. This 1 minus m kg is flowing in stage 2. So and the change in enthalpy is H2 minus H3. So the same thing we'll write for the WT2 here. So that is 1 minus m into H2 minus H3. So this is the turbine work formula. So where m is mass of the steam bled, and which is unknown, to find m we know from the theory discussions on regenerative Rankine cycle. So we apply where m is mass of steam bled from turbine at 2. So then to find m, apply energy balance to OFH, that is open feed water heater. So here to find the mass m, so I will separate the open feed water heater from this schematic diagram, and I will redraw it for our better understanding. So here I will redraw the open feed water heater, that is OFH, and we have one inlet stream with 1 minus m kg of steam, and the inlet enthalpy is HFI, and we have one more inlet stream, that is m kg with H2 enthalpy, and one outlet stream for the open feed water heater, that is with HF6. So why F is used? Because the working fluid is in liquid state at these two states. So now applying energy balance for this, so that is m into H2 plus 1 minus m into HF5, so which is equal to HF6. So now we have to substitute the enthalpy values that are known to us. So here H2, he has given in the given data H2 as 2500 kilojoule per kg from the given data. So I would substitute the same value from the given data, that is m into 2500 plus 1 minus m into HF5. HF5, what is HF5? So HF5 is enthalpy at state 5, so it is also given in the given data, this is given as 125 kilojoule per kg. So let us substitute the same value in the equation, so which is equal to HF6, that is enthalpy at state 6. So here in the given data, enthalpy at state 6, that is nothing but the enthalpy of saturated liquid at state 6. So how to get enthalpy of saturated liquid at state 6 is nothing but the HF value at the operating pressure of open feed water heater. So what is the operating pressure of open feed water heater? It is the pressure of the steam which is supplied in it. So what is the pressure of the steam? So pressure of the steam is 3.2 bar. So hence the same pressure is maintained at 6 as well as at the inlet here. So hence the HF6 will be equal to HF at 3.2 bar. So that is HF at 3.2 bar. So we need to obtain this value from the steam table. Now from the steam table, here we have saturation pressure column. So at 3.2 bar, the value of HF is 570.9 kilojoule per kg. So let me substitute the same value M 2500 plus, I'll open the bracket now, 125 minus 125 M, so which is equal to 570.9 from the steam table. So here let me solve this equation for M. So if I simplify, so I'll get it as 1975 M, which is equal to 570.9 minus 125. So therefore M, if I operate the calculator, so I'll get it as 0.226 kg of steam bled for every 1 kg of steam supplied to the turbine. Means if I am supplying 1 kg at the inlet of the turbine here, at the inlet of the turbine, so I am bleeding 0.226 kg, that is 226 grams of steam is bled out of this. So here we are able to calculate the value of the M, that is mass of steam bled for every 1 kg of steam that we have supplied. Now the steam supplied to the steam turbine per hour we need to calculate, that is mass flow rate of the steam. So we don't want the mass M, mass of the steam bled M, so we want the M dot S, that is mass of the steam bled for 1 hour, per hour or per second. Let's calculate that one. So if we supply 1 kg, how much we are bleeding? So we are bleeding 0.226 kg, means for bleeding 0.226 kg of steam from the turbine, how much we are supplying? We are supplying 1 kg of steam into the turbine. But for every hour, for bleeding 11,200 kg of steam in 1 hour, so how much steam we have to supply at the turbine inlet? That is mass flow rate of steam is equal to question mark. So if we apply the cross multiplication, so therefore I can write m dot s is equal to 11,200 kg per hour divided by 0.226 kg of steam bled per kg of steam supplied to the turbine. So here kg of steam and kg of steam cancels. So kg of steam supplied in 1 hour for the turbine, that is mass flow rate of steam supplied to the turbine. So here if we operate the calculator, so we will be able to get m dot s as 49,557.5 kg of steam is supplied for every 1 hour into the turbine. So thus we calculated the mass flow rate of the steam. Now we are remained with the turbine work expression that we had written. So that is turbine work was written as this formula. So let's substitute the known values in this equation and calculate the turbine work. So therefore turbine work, I will write it, this equation once again, 1 into h1 minus h2 plus 1 minus m into h2 minus h3. So here 1 into h1 he has given in the problem statement in the given data enthalpy, that is h1 as 3100. So I will substitute the same value here minus h2 he had given as 2500 kilojoule per kg. So I would substitute 2500 kilojoule per kg plus 1 minus m we have calculated it as 0.226. so I will substitute the same value 0.226. h2 I will take it as 2500 minus h3 he has given it as in the problem statement given data 2100 kilojoule per kg. So I will substitute the same as 2100 kilojoule per kg. So if I operate the calculator, so I will get this as 600 plus this as 309.6. So the total is 909.6 kilojoule per kg of steam supplied. Means this turbine is able to develop 909.6 kilojoule of turbine work when 1 kg of steam is supplied into the turbine. So we calculated turbine work in the power equation. So we wanted to calculate power. So this is the net W net into m dot s, and it was finally the net work into m dot s. Now we calculated both turbine work as well as mass flow rate of the steam. Now let us substitute this as power is equal to Wt into ms m dot s. I am writing it once again. So Wt is 909.6 kilojoule per kg into the m dot s is, so we have calculated it as 49,557 49,557.5 kg per hour. So we'll cancel kg of steam and kg of steam to convert this hour into seconds. So we know that 1 hour is 3600 seconds it is. So then if we operate the calculator, so the power is, we are able to calculate it as 12,521.5 kilowatt. So kilojoule per second is kilowatt it is. So this is the required answer. Let's discuss one more problem on regenerative Rankine cycle. Let's understand the problem statement first. In a single heater, means only one heater is there, and in a regenerative Rankine cycle, the steam enters the turbine at 30 bar pressure and 400 degrees Celsius temperature. The exhaust pressure is 0.10 bar. So regenerative Rankine cycle with single feed water heater. So let me draw the schematic diagram for our better understanding of the problem statement. So in a single feed water heater we have a boiler. So from the boiler it is entering the steam turbine. So here I have stage 1, this is stage 2. So the inlet is state 1. Here I am bleeding at state 2 into a single open feed water heater. So I am writing it as OFH, so which supplies the steam from bleeding the steam turbine casing. Then the steam expands from 2 to 3 in the second stage. So from 3 onwards it enters the condenser. So from condenser again it enters a pump. So pump pumps the condensate against the pressure inside the open feed water heater. This is state 4, this is state 5. So in feed water heater both get mixed and the condensate comes out at state 6. From here it enters a pump. So this is the schematic diagram for open feed water heater here. So here he has given the condition, that is P1 is equal to 30 bar and T superheat 1 equal to 400 degrees Celsius. So 400 degrees Celsius it is a superheat temperature at 30 bar. Then again the exhaust, how we determined this as a superheat means, if you open the steam table, look at saturation temperature against 30 bar, so it is definitely less than 400 degrees Celsius. The exhaust pressure is 0.1 bar, means the steam turbine, after the pressure after coming out of the steam turbine or condenser inlet pressure is here, this is 0.1 bar. The feed water heater is a direct contact type, so it is a direct contact type. So both blood steam as well as condensate both are mixing directly. So which operates at 5 bar, means the pressure is 5 bar. At the open feed water heater it is 5 bar pressure, that is P2 is equal to 5 bar pressure. This is P3 condenser pressure. Find the thermal efficiency and steam rate for the cycle. So we need to find out thermal efficiency as well as steam rate. So now here we have the second bit of the problem, so wherein he is asking us to calculate increase in mean temperature of the heat addition, that is mean temperature of heat addition. So we'll discuss in while solving the problem. Then again increase in thermal efficiency of the plant and steam rate, increase in the steam rate as compared to the basic Rankine cycle, that is the cycle without regeneration. Means we need to calculate the efficiency, steam rate and mean temperature of heat addition for a simple cycle, that is without regenerator, that is simple Rankine cycle. So we need to calculate the increase in all these parameters, so when we run the plant with regenerator, and he is asking us to calculate neglect the pump work in this problem statement. So now for our better understanding, let's draw the TS diagram and HS diagram for the present problem. The TS diagram, we know that temperature, entropy diagram, this is the vapor dome. So we have the superheated steam at turbine inlet, so it undergoes expansion till state 2. So from 2, a steam is bled at P2 pressure, P2 is equal to 5 bar pressure, and m kg is bled, and after 2 it enters the second stage of the turbine, it undergoes expansion till 3. So here it was 1 kg, here 1 minus m expands, so that is on the TS diagram also, here 1 kg is expanding, here 1 minus m kg is expanding because I have bled m kg from this. So 3 to 4 I have the condensation, 3 to 4 I have the condensation, so 4 to 5 we have pumping work, so 5 to 6 it's a open feed water heating, 5 to 6, and 6 to 7 that is boiler pumping work. So 6 to 7 pumping work. So 7 onwards the heat is applied inside the boiler and it gets heated. So this is how TS diagram is drawn for the present problem. So this is P1 30 bar, P2 5 bar, and P3 is 0.1 bar pressure. So here HS diagram also can be drawn, that is molar chart. This is the enthalpy entropy diagram. So here I have the saturation curve, and we have the condenser pressure P3 is equal to 0.1 bar, and we can identify one more temperature line, that is a pressure line, that is P1 equal to 30 bar on the molar chart or HS diagram, and we have a constant temperature line of 400 degrees Celsius. So wherever both the lines intersect, we can fix this as state 1. So from state 1, since 1 to 2 is isentropic expansion inside the turbine, so we can draw a vertical line in the downward direction. So it expands till 2. So from 2, that is 2, the second pressure line is 5 bar, that is P2 is equal to 5 bar, until 5 bar it expands. So 2, but the quantity was 1 kg here. Now we are bleeding m kg out of this. So here it was 1 kg, m kg out of this. Now remaining 1 minus m kg expands till 0.1 bar pressure line on the condenser. So now here we have 3 to 4 condensation till it becomes a saturated liquid. 3 to 4, so 4 to 5 again pumping, 4 to 5 pumping, 5 to 6, 6 to 7 4 5 6 7 it is. So this is how HS diagram can be drawn, and with the same process on the molar chart, so we'll be able to get H1 value, and here I am able to get H2 value on molar chart, and we can get H3 value on y-axis. So now let's look into the solution. First one is we need to calculate the thermal efficiency for the regenerative Rankine cycle with all these operating parameters. So now here first let's look into thermal efficiency with the given data for this plant. That is the thermal efficiency. We know that first bit of the plant, that is thermal efficiency of the plant. Thermal efficiency is always given by the net work upon heat supplied. That is thermal efficiency is equal to net work upon heat supplied. So in this case, turbine work minus pump work divided by heat supplied is Q1, means we are supplying Q1 amount of heat energy inside the boiler, and we are rejecting Q2 in condenser. So that is a thermal efficiency expression. And pump work we consider it as 0 because here is given data. This is given data, that is to be neglected. So the final expression is turbine work upon Q1, that is heat supplied, is the thermal efficiency expression. So if you look into the turbine work in the schematic diagram itself, so here this is the turbine 1, this is turbine 2. So this produces WT2 and this produces WT1. The total turbine work is WT is equal to WT1 plus WT2, and means we need to calculate first the turbine work. Turbine work WT is equal to WT1 plus WT2. So now here in the schematic diagram, turbine 1 is operating between 1 and 2. The inlet enthalpy is H1, exit enthalpy is H2, and the fraction of steam or the volume of steam, mass of the steam which is flowing in the turbine 1 is 1 kg. So we know the turbine work is change in enthalpy, that is 1 into H1 minus H2 plus WT2 is the inlet enthalpy is H2 and exit enthalpy is H3. The mass of the steam flowing inside the stage 2 is 1 minus m. So that is 1 minus m H2 minus H3 is the formula for turbine work. Means in the problem statement nowhere he has mentioned m. So m is, we have assumed in the schematic diagram, m is the mass of the steam bled after stage 1. So now we need to calculate H1, that is enthalpy at the inlet of the turbine, H2, that is enthalpy of the steam at state 2, then H3, that is enthalpy at turbine outlet. So these values are unknown to us, even we don't know the value of m also. So let's obtain these values either from molar chart. So there are two methods to obtain these values. So first one is using steam tables, or second one is using Molière chart. So we can use any one of these methods to find out the values of enthalpy, that is H1, H2, H3. So now let's prefer the first method to understand ourselves how to calculate these enthalpy values using steam tables. So for calculation of these values, let's refer the steam table and note down the properties of steam at P1 pressure, P2 pressure as well as P3 pressure. So that is at P1 pressure, so what are the properties, and at P2 pressure what are the properties, and at P3 pressure what are the properties, that is entropy values and enthalpy values. So we'll note down and we'll analyze these processes to get the unknown values, that is enthalpy values, to calculate the enthalpy values. Now from the steam table at 30 bar at P1 is equal to 30 bar and 400 degrees Celsius, we can get the enthalpy value H1 and entropy value S1 as, see, now let's look into the steam table. So here I have superated steam table for specific enthalpy. So this is the pressure column. So I have 30 bar pressure, and these are the superate temperatures. So at 400 degrees Celsius, so I will look for 30 bar pressure here. So here for 30 bar pressure, so the saturation temperature is 233.8 degrees Celsius. So the given temperature is 400 and the steam temperature is 400 degrees Celsius, so which is higher than the saturation temperature 233.8 degrees Celsius. Hence the steam is in superated condition. So now at 400 degrees Celsius, so if I move downward at 30 bar pressure, so I have enthalpy as 3232.5 kilojoule per kg. Now again we have the specific entropy for the superated steam. So now on the pressure column, if I come for 30 bar pressure line, and on the temperature line we have 400 degrees Celsius, so I have to come downward against 30 bar pressure. So here I have for 30 bar pressure the entropy under 400 degrees Celsius column, it is a 6.925 kilojoule per kg Kelvin. Now we got H1 as 3232.5 kilojoule per kg and S1 as 6.925 kilojoule per kg Kelvin. So now as the processes in this regenerative Rankine cycle are isentropic in turbine stage 1 and turbine stage 2, that is 1 to 2 is isentropic process, entropy remains constant, and again that is S1 is equal to S2, and again 2 to 3 is isentropic expansion in turbine stage 2, here also entropy remains constant, so that is S2 is equal to S3. So I can write on this S1 is equal to S2 is equal to S3, so that is which is also equal to S2 and S3. So now here let's note down the properties at 5 bar pressure from the steam table. At 5 bar pressure from the steam table. Now at 5 bar I have HF value 640.1, Hg value 2747.5, and again I have Sg value 6.819 kilojoule per kg Kelvin. That is at 5 bar we have HF as 640.1 kilojoule per kg, Hg as 2747.5 kilojoule per kg, then Sg, that is entropy value 6.819 kilojoule per kg Kelvin it is. So similarly at P3 is equal to 0.1 bar, that is condenser pressure, so we will be able to note down HF value as 191.8 kilojoule per kg, then SF value 0.649, Sg as 8.151 kilojoule per kg Kelvin, SFG 7.502 kilojoule per kg Kelvin. So these are the properties that we noted down, which will be useful for our further calculations. Now let's note down the enthalpy values. So we got H1 value directly from the steam table, that is 3232.5 kilojoule per kg. This is the H1 value. Now let's calculate the H2, that is for H2 enthalpy value. For H2, so as we are solving from the steam tables, so we need to apply the required formulae for calculation of this H2. So now for calculation of enthalpy at state 2, we must know what is the condition of the steam at state 2. So at state 2, so we don't know exactly whether state 2 is a superheated steam or saturated vapor steam or wet steam. So we don't know exactly what is the condition. So to determine, we'll compare the entropy values. So that is the entropy value at state 2. The entropy value at state 2 on the TS diagram. Entropy value at state 2, we have understood at state 2 S2 is equal to S1, so which is equal to 6.925 kilojoule per kg Kelvin. That is the entropy value at state 2. Now let's check the Sg value at 5 bar. That is here on this TS diagram SG value. This is the SG value at TS diagram, that is at point 2, that is 5 bar pressure. So SG value at 5 bar pressure is 6.819, so which is lesser than the entropy at state 2. So therefore the entropy at state 2 is greater than the entropy of the saturated vapor, that is 6.819 kilojoule per kg Kelvin at P2 pressure, that is 5 bar pressure. So hence we can conclude from this statement that, see, the SG value on the TS diagram, SG value here I have got 6.819 as an entropy, but at state 2 it is 6.9, here it is 6.8, so hence the state 2 is beyond the saturated vapor line, so hence state 2 is superheated steam. So therefore this condition gives me that the steam is superheated at state 2. So now since the steam is superheated at state 2, so I have to apply the formula to calculate the enthalpy at state 2 using above properties. So on the TS diagram, so we have entropy values and temperature values and few enthalpy values from the steam table. So we have to calculate the enthalpy at state 2. State 2 is superheated state. So on the TS diagram it is, so state 2 is superheated state. So the enthalpy at state 2 can be written as enthalpy on saturated vapor line, that is Hg2 plus the change in enthalpy during superheating, that is Cp into the change in temperature. So here I have Ts2, that is saturation temperature at 5 bar, and here I have Ts1, that is saturation temperature at 30 bar. So now we have saturation temperature at this one, and again we have the superheat temperature at state 2, this is T superheat 2, and I have a T superheat temperature 1. So if you look into this formula, so I need to get the temperature values to calculate the enthalpy at state 2. So for saturation temperature values we can get from the steam table, and the superheat temperature can be calculated from the entropy equation. Let's look into the solution. Now here at 30 bar we have the saturation temperature, that is Ts1 from the steam table, that is 151 233.8 degrees Celsius, and we have Ts2 from the steam table, that is saturation temperature at 5 bar 151.86 degrees Celsius. So then again this is the temperature. We have to calculate the superheat temperature at state 2 to calculate the enthalpy at state 2. So first of all, let's write the expression for enthalpy at state 2. So enthalpy at state 2 can be obtained using the formula, that is H2 will be equal to Hg2 plus Cp into T superheat 2 minus T S2. So I will write the same expression because since I want H2, that is enthalpy at state 2, so enthalpy at state 2 can be written as Hg at state 2 plus the superheat enthalpy, that is Cp into T superheat at 2 minus T saturation at P2 pressure. So now here that is nothing but Hg at 5 bar pressure Cp into T superheat 2 minus T saturation 2. So we have the specific enthalpy Hg at 5 bar as this value. So we'll substitute in this 2747.5 plus Cp, we can take it as 2.1 kilojoule per kg Kelvin for the superheated steam, but we don't know the superheat temperature at state 2, but saturation temperature is known to us, that is 151.86 degrees Celsius. So now here we need to calculate the superheat temperature too. So how to calculate this one? So for T superheat to consider the process 1 to 2, and for 1 to 2 it is an isentropic process, so hence I can write S1 is equal to S2, and we know that the state 2 is a superheated steam. So for superheated steam, the specific entropy formula is S1 is equal to S2. I am replacing with Sg2 plus Cp ln of T superheat 2 upon T saturation 2. So this is the formula from basic thermodynamics, that is we know already. So now we have the values, that is S1 equal to S2, that is the value 6.925 kilojoule per kg Kelvin. So I will substitute the same value here, 6.925 kilojoule per kg Kelvin, and this is Sg at 5 bar plus Cp ln T superheat 2 and T saturation 2. So now 6.925 is equal to the specific entropy at 5 bar Sg value is 6.8 6.819 kilojoule per kg Kelvin, 6.819 plus Cp is 2.1 ln of. Now I have to substitute Kelvin temperature whenever there is a ratio of temperature in Kelvin, that is T superheated to. So I am supposed to calculate T superheat 2 only, so I will keep it as it is, divided by T saturation 2. T saturation 2, that is at 5 bar, I have 151.86 degrees Celsius, so I will substitute it as 151.86 degrees Celsius plus 273 I will add. So whenever we divide, so we need to substitute the temperature in terms of Kelvin. So now after operating the calculator, so I will be able to calculate T superheat temperature as 173.79 degree Celsius. So hence I will be able to calculate H2 now. So that is H2 is equal to 2747.5 plus 2.1 into 173.79 minus 151.86, so which is obtained as 2793.55 kilojoule per kg. So now I got the H2 value. So this is a repetitive procedure that we know already from the basic problems on Rankine cycle. So similarly, I need to get or calculate the enthalpy at state 3, that is H3 value is required for me, because in turbine work formula I obtained H1 value and H2 value now, but I need H3 value also. So for getting H3 value, let me consider the process 2 to 3 and apply the formulae and calculate H3. Now for H3, so I will consider process 2 to 3. Now here we have S2 is equal to S3, since this process is isentropic, and we can write this value as 6.925 kilojoule per kg Kelvin. So now we will compare this entropy value, that is specific entropy at state 3 is equal to 6.925 with the specific entropy value, that is SG is equal to SG at 3 is equal to 8.151. So we have noted down in the steam table, from the steam table, SG at 0.1 bar as 8.151 kilojoule per kg Kelvin. So in the TS diagram, so this is the S3 value here, S3 value, that is 6.925, and we'll compare the value at here, that is SG3, so which is equal to 8.151. So therefore the entropy at state 3 is lesser than SG3, so means it is moving towards the wet region on the vapor dome. So hence we can write the same expression, that is specific entropy at state 3 is less than the specific entropy of the saturated vapor, that is 8.151 kilojoule per kg Kelvin. So therefore the steam is wet steam at 3. So once we understood the steam is wet at state 3, so we need to apply the specific enthalpy formula at state 3 to calculate its enthalpy. So once we know the state 3 is in wet region, so I have the dryness fraction x3 here, and we have HF at this 0.1 bar pressure, HF at 0.1 bar pressure, and we have HFG values at 0.1 bar pressure. So the enthalpy at state 3, that is H3, we know the formula. H3 can be calculated as HF3 plus X3 into HFG3. H3 into HFG3, the same formula, so we can write here, that is H3 is equal to HF3 plus X3 into HFG3. So or enthalpy at state 3 is equal to HF at 0.1 bar plus X3 into HFG at 0.1 bar. So we have these two values, but X3 is unknown to us. But we don't know the X3 value in this. So for getting X3 value, we can apply the formula, that is S2 is equal to S3, that is S2 is equal to S3. So since steam is wet at state 3, so I can write it as S2 is equal to SF3 plus X3 into SFG3. So now here I have SF3 0.649 plus X3 into 7.502. So now we have S2 as 6.925. So therefore after operating calculator, so I'll be able to get X3 as 0.836. So now let's calculate the H3 now. So H3 is HF, that is at 0.1 bar from the noted values. So we have, these are the properties at 0.1 bar. You can pause and check the values. These values I am going to substitute here. So that is H3 HF at 0.1 bar, I am going to substitute it as 191.8 plus X3, we have obtained it as 0.836 into 2392.9. So that is HFG at 0.1 bar. So we have substituted. So finally I'll be able to calculate S3 as 2192.36 kilojoule per kg. So this is the H3 value. So we can also calculate the H4 and H6 values, so which will be required for our further calculations. So H4 is nothing but the HF at 0.1 bar from the TS and PV diagram, TS and HS diagram, so we can understand. So HF4 is nothing but HF at P3 is equal to 0.1 bar pressure line. HF4 is equal to HF at 0.1 pressure line. So therefore H4, from the steam table I will write H4 is equal to HF at 0.1 bar pressure line, so which is equal to HF at 3 also you can say, that is 191.8 kilojoule per kg, and H6, that is enthalpy at state 6, also we can write, that is enthalpy at state 6 is nothing but the enthalpy of saturated liquid at pressure 5 bar, that is HF at 5 bar, that is HF at 5 bar. From the property table we have noted down this value also as 640.1 kilojoule per kg. So after obtaining all these values, we don't know the value of M in the turbine work expression. So in the turbine work expression we calculated H1, H2 and H3, but M is also unknown to us. M is the mass of the steam bled out of the turbine. So how do we calculate the mass of the steam bled out of the turbine? Using open feed water heater, applying energy balance across the open feed water heater, we calculate the value of M. So let me calculate the value of M so that we will be able to calculate the turbine work, which is essential to calculate the thermal efficiency. So here, for obtaining the thermal we'll calculate the mass of the steam blade applying the energy balance across the heater. So that is energy balance across open feed water heater. So we have open feed water heater as M into H2 here as an inlet, and again we have HF5 1 minus M is here, both are inlet, and I have HF6 at the exit with 1 kg here, that is 1 minus M1 plus M, both cancels. So after applying that, so I have the energy balance equation, M into H2 plus 1 minus M HF5, which is equal to 1 kg into HF6. So after, let me simplify this one with simple mathematics. M H2 plus 1 minus M HF4 I am going to write, because HF5 is the enthalpy at 5, which is also equal to enthalpy at 4, because pump work is negligible here, so I am replacing it with HF4, so which is 1 into HF6. So now I'll write M into H2 plus, I'll open the bracket, HF4 minus M HF4, which is equal to HF6. So I'll take M common out of these two terms, M into H2 minus HF4, so which is equal to HF6 minus HF4. So therefore mass of the steam blade, so I'll write the expression HF2, that is I can replace this HF as HF2, HF6 as HF2 minus HF3, that is HF4 as HF3. So why I am replacing these two terms means HF2 is the HF value at 5 bar pressure, so that is from here HF value at 6 and HF value at 0.2 both will be same, because the pressure is 5 bar. At 5 bar pressure, if you read the HF value, it is the same for state 6 as well as state 2. And similarly, so I am replacing HF4 with HF3. So since the value of HF at 0.1 bar at state 4 and state 3 will be same. So we have seen from the steam table at 0.1 bar the HF value at we have read, so it would be remain same. So hence after replacing that, so mass of the steam blade is HF2 minus HF3 divided by H2 minus HF3. So I will substitute these values, that is HF at the pressures 640.1 minus 191.8 divided by 2793.85 minus 191.8. So I will be able to calculate the mass of the steam blade as M is equal to 0.172 kg of steam, which is bled. Now the turbine work can be calculated from the calculated data. So we have already written it is 1 into H1 minus H2 plus 1 minus M into H2 minus H3. So we'll substitute the data, that is 1 into H1 is 3232.5 minus H2 we have calculated as 2793.5 plus 1 minus 0.172 into bracket 2793.5 H2 minus H3 is 2192.26. So we'll be able to calculate it as 439 plus 0.8282 to 601.24. So finally the turbine work is 936.8 kilojoule per kg. So now let's calculate the heat supplied for calculation of thermal efficiency. So that is Q1. So Q1 where we are supplying inside the boiler. So in boiler we have the heat supply between 1 and 7, that is Q1 is equal to H1 minus HF7. Same formula let me use for the heat supply here. So that is Q1 is equal to H1 minus HF7, so which is also equal to H1 minus HF6, since pump work is negligible and we know the HF value at 6th state. Let me substitute. Q1 is equal to H1 is 3232.5 minus we have HF6 as 640.1, that is HF at 5 bar pressure 640.1. So with this Q1 is 2592.4 kilojoule per kg. So now we'll be able to calculate the thermal efficiency. So therefore thermal efficiency is equal to WT upon QS, that is 936.8 divided by 2592.4, this is 0.36136. So therefore thermal efficiency is 36.13%. So he has also asked us to calculate steam rate, that is steam rate, we know the formula, it is 3600 divided by the turbine work 936.8, so which is 3.842 kg per kilowatt hour. So this is the solution for the first bit. So let's have a quick review. So in the problem statement we were supposed to calculate thermal efficiency and we knew this formula, and against this we wrote the turbine efficiency turbine work formula. So wherein H1, H2, S3 were unknown. So to calculate these values we followed the steam table method by noting down all the properties. This was all the discussion to calculate the H2. So then again for calculation of H3, so we had one more discussion. So this was the discussion for calculation of H3. So if this is a lengthy procedure, so we can also get H2 and H3 values, H1, H2, H3 values from the Mollier chart. So that is on the Mollier chart. So first after obtaining the Mollier chart, so we have enthalpy values on y-axis, entropy values on x-axis. So we have a saturation vapor line. So from the given data, so we know that first we need to mark the state point 1 on the Mollier chart. So we have the 30 bar pressure line, if we identify 30 bar pressure line on the molar chart, and we have 400 degrees Celsius constant temperature line, wherever both intersect we can mark this as 0.1. So we'll be able to get H1 value, so which is almost 3200 kilojoule per kg on the molar chart. So now here, since isentropic expansion is happening till 5 bar, so we need to drop a vertical line downward on the molar chart, so till 5 bar. So wherever both intersects, so I can mark this as a state point 2. So if I drop a horizontal line towards y-axis, so I'll be able to get H2 value. So H2 value is around 2790 on the molar chart. 2790 on the molar chart. So similarly, so until 0.1 bar pressure line, 0.1 bar pressure line, so if I draw a vertical line, I can mark this as a state point 3. So I will be able to calculate H3. So H3 is 2190 on the molar chart. So this method of using molar chart reduces your calculations and will also give the similar values of answers. So to save the time in exam, if a given data is suitable to use the molar chart, it is better to use molar chart to reduce the time in the exam. So after that we calculated the mass of the blood stream, and finally we calculated the turbine work, then heat supplied, and then the thermal efficiency as well as steam rate. Now we have the second bit of the problem, so wherein we need to compare this open feed water heater regenerative Rankine cycle with simple Rankine cycle. So for that reason, let me draw the simple Rankine cycle with the same notations, so that we can utilize the values that we have already calculated in the present problem. So keeping the same notations, how I can modify this cycle. So here I have the regenerative Rankine cycle with open feed water heater. This is boiler. So here I have the turbine. So state 1, this is state 2, here state 3, this is condenser. So after this we have the bleeding. So OFH is here open feed water heater. So we have a pump, so which pumps into this. So the outlet of this enters a pump. So this was entering. So this is 4, here I have 5, then I have 6th state, this is the 7th state. So now the same cycle to be modified as a simple Rankine cycle with the notations. So I have the boiler here. So from this it will expand in a steam turbine. So I have one at the inlet. So here I have state 2, but I am not taking it into any open feed water heater. So here I will take it as a state 3. So state 3, it enters the condenser. So from the condenser we have a pump, so which pumps directly into the boiler. So this is 3 to 4 and 4 to 5, we can say. That is pump work here, so which is negligible. WP is equal to 0. So here also WP is neglected, WP is neglected in both cases. So now if we look into the TS diagram, if we look into the TS diagram, where we are adding heat energy, we are adding heat energy between 7 and 1. So Q1 can be written as the area below this process line. So that is, so the temperature is continuously changing from 7 to 1. So let us take it as a mean temperature Tm, and so Q1 can be written as Q1 is equal to, that is H1 minus HF7 is equal to Tm into the change in entropy, that is S1 minus S7. So we can write it as Q1 is equal to H1 minus HF7, so which is equal to mean temperature into S1 minus S7. So therefore we can calculate mean temperature as H1 minus HF7 divided by S1 minus S7. What is S7? S7 is the entropy SF at 30 bar pressure. So hence we can write mean temperature as H1 minus HF7 divided by S1 minus S7. So S7 we can take it as specific entropy at 6, that is S6, so which is nothing but the specific entropy at 5 bar. So hence let's substitute the values, that is H1 minus HF7, if you subtract, so if we substitute, so we'll be able to get in Kelvin mean temperature as 511.82 and in degree Celsius 238.8 degree Celsius for the regeneration cycle. Now let's calculate the mean temperature without regeneration. So without regeneration, TS diagram gets modified like this: 1, 2, 3. So 4 to 5 pump work is negligible, and 5 to 1 we are adding Q1 heat energy. So therefore Q1 can be written as mean temperature of heat addition, that is Tm into S1 minus S4. So with substitutions, so we will get mean temperature as 484.1949 Kelvin and mean temperature as 211.49 degrees Celsius. Increase in mean temperature is 27.3 degrees Celsius. This is the steam rate without regeneration. H1 minus H3 WT we calculate. So then we calculate the regeneration, increase in the steam rate. So then again thermal efficiency gets modified according to new cycle. So this is the new thermal efficiency. So just pause this video and please go through the steps. Thank you.